Hello, my name is Adrian Lupascu. I am a researcher at University of Waterloo, and I'm going to talk about our plans to take quantum control to the next level. Quantum computing is usually done with qubits or two-level systems. Using qubits provides a convenient framework to analyze quantum algorithms and quantum error correction. However, most physical systems used to implement quantum computers are multi-level systems, and the usual approach is to use the lowest two energy states to encode the qubit and then find ways to avoid excitation to higher levels. An interesting question that arises is, can we make use actually of these multiple states? This question has been explored to some extent in the field of superconducting devices with applications to 2-qubit gates, but we want to take things even farther. We want to develop a research program that takes a unifying view of using multi-level systems, including quantum algorithms, quantum error correction, and physical implementation. This research would use three types of approaches. The first approach is to develop new device designs that are informed by optimal quantum control. Superconducting devices provide a rich playground for this type of work, but this is applicable to other platforms, including ion traps and spin memory elements as well. The second approach is to encode information in qubits or multi-level systems. This is appealing due to high error correction thresholds. And one interesting challenge here is to make the connection between abstract theory and experimental implementation of such platforms. The third type of approach is to still encode information in qubits, but use additional levels and multi-level systems to enable more efficient gate decompositions. This project has been discussed so far by a group including, besides myself, Barry Sanders at University of Calgary, John Yard at University of Waterloo, and Felix Mozzoy and Tommaso Cadarco in Jülich. These groups brings together a broad range of expertise in quantum information theory, quantum control based on different strategies, experimental control in multi-level systems. We're also looking to develop collaborations, in particular in the area of hardware for scalable quantum control, which is a strength in the EU. We expect this project to have an impact in high-fidelity qubit control, improve quantum computer designs, control software and hardware adapted to multi-level systems, and finally, we hope that this work will have an impact for fault tolerance in the post-NISQ era. We welcome questions and ideas from colleagues and interest in collaboration. Please feel free to contact any of us. And with this, thank you for your attention.